So we've got these already memorized, okay? But we're missing a couple functions, right? So we're going to expand our anti-differentiation knowledge by memorizing, again, memorizing, because you already have these, no problem. Now we're going to memorize a few more, all right, the other trig functions. So there's some neat ways to do this clever, all right, being clever. Maybe you could do A and B. C and D, it's not as intuitive, all right? But you do know that another way to write tangent would be to write sine over cosine. Okay, and even another way would be to write that as sine times 1 over cosine. All right, so now, wait, I have the derivative of cosine, that's negative sine, so I just have to correct for this. Now, how do I do the antiderivative of 1 over something? Well, that would be just ln. So ln, absolute value of cosine of x, plus c. There you go. This is the antiderivative of tangent. Now, another way to write that using your rules of logs, right? I could put that up there, and then I could also flip the inside. All right, so that would be 1 over cosine on the inside, or secant. So you might see this either way. You might see it this way, or you might see it this way. Okay, either way, and you can use either form. Now, cotangent, we can use this similar method. That's cosine of x over sine of x. I could rewrite that to maybe make it a little bit more clear. The derivative of sine of x, I know, is cosine of x. So I don't have any corrections here. It's just ln of sine of x plus c. All right, or I could flip over the sign, so it's like 1 over sine of x. So that would make the power -1, or stick it in the front. So I could have also negative ln of cosecant of x plus c. And those are the different forms that you could see that in. All right, this one is not as intuitive. This is something that would be a lot easier if you would just memorize it. So we need to, if we write 1 over cosine of x, it doesn't help at all. Oops. If we try to use an identity, we're not going to get anywhere. So you have to multiply by an intuitive form of 1. Okay, since your intuition may not be that great right now, I'm going to help you out. You multiply by secant x plus tangent x over secant x plus tangent x. Now, the reason why you would want to do that is because this now becomes secant squared x plus secant x tangent x over secant of x plus tangent of x dx. All right, why is that useful? That looks even worse, right? But let me get my highlighter so we could talk about this for a second. The derivative of secant of x is secant x tangent x. The derivative of tangent of x is secant squared x. So now we have that derivative on the top, okay, and then it would look just like the problems we did before. Let me change that, okay, just like this one, where our function was in 1 over our function times the derivative. So this is going to be ln of secant x plus tangent of x. All right, plus c. Okay, again, for this one, we're going to use the same kind of idea. We're multiplying by a clever form of 1. Whoa, that messed up. Okay. We're going to multiply by cosecant x plus cotangent x over cosecant x plus cotangent x. And the reason why we'd want to do that, now we're going to get cosecant squared x plus cosecant x cotangent x all over cosecant x plus cotangent x. Okay, don't forget that dx there. All right, now the derivative of cosecant is negative cosecant x. Right? Alright, sorry about that. The derivative of cosecant of x is negative cosecant x cotangent x. Derivative of cotangent of x is negative cosecant squared of x. So we're only off by a negative, so we'll put that correction there. And ln of cosecant x plus cotangent x plus c. There we go. Alright, so we have all these different things that you need to memorize. Okay, so make sure that you have these things memorized. Then we can use them. So once you have them memorized, it's easier to use. So we have this function. Looks kind of scary, alright, but not too bad. Pull that constant out. Look, it looks even easier now. We now know, before you wouldn't have been able to get too far, but because we know the antiderivative of tangent now, this makes this problem a little bit easier. Alright, so we have 5. The derivative of the inside would be 3x squared, not just x squared. So we have to correct for that. Alright, now the derivative of tangent is just negative ln of secant x squared plus, or x cubed, sorry, plus 1. Okay, plus c. There you go. And if you wanted, you could have put the cosine in there. Alright, so I made a problem. I'm mixing up two different things here. That's a giant eraser. That's alright. I would either put the negative and cosine, or just put secant. So it's your choice, alright? Or if you want to use the other form, you could do 5/3 times negative ln absolute value cosecant of x cubed plus 1 plus c. There we go. Alright, got it all. This is another problem that I can also do, where you couldn't have done it before. I'm going to pull the 2 out. Alright. And then I have e to the negative x times secant of e to the negative x. Well, the derivative of e to the negative x would be negative e to the negative x. So I have this correction here. And then I already have this part taken care of. I'm just focused on this. Derivative of secant would be ln, absolute value, secant, e to the negative x plus tangent, e to the negative x plus c. Alright, and if you wanted to rewrite it as negative 2 times that, no problem. Alright, so now we have this nice base of things that we can do. Alright, so we'll use pattern recognition if you can, or U-Substitution, either is fine. I'm going to rewrite this for a second. X times 1 over x squared minus 4. So the antiderivative, or actually the derivative of x squared minus 4, if I think about that, that's just 2x. So I'm only off by a constant. Alright, I'm going to correct for that constant by putting 1/2. And now this would just be ln of x squared minus 4 plus c. Alright, that one's not that bad. I'm going to skip part B because that's what you'll do for your whisk. Alright, part C. Oh, that's ugly. I'm going to rewrite it. I'm going to bring out that 1/4. I'm going to write this 1 over x times ln of x to the 2/3 power. Alright, so I notice the derivative of ln of x is 1 over x. Okay, and I already corrected for that 1/4. There's no other corrections here, so I have 1/4 times. And now I'm just going to use the power rule. Add 1 to the power. Okay, we get 5/3. So we're going to multiply by 3/5, not 5/3. There we go. 5/3 multiplied by 3/5 plus c. Alright, so if you want, you could write it as 3/20 ln of x, 5/3 to the 5/3 power plus c. Alright, this one is really easy if you know what you're doing. Alright, pull out that 1 over e. We don't need that there. That's 1 over x times cosecant x, not cosecant x, cosecant of ln of x dx. Okay, so I have 1 over e. The derivative of ln of x is 1 over x, so I don't have to correct for anything. And now it's just the antiderivative of cosecant, which you have now memorized. Okay, so then that would be negative ln cosecant x plus cotangent x plus c. All right, and if you want to rewrite it, feel free. I'm not going to worry about it. This one's kind of neat. So I'm going to rewrite it down here. I'm going to just also rewrite it this way. Now, if we think about this a little bit, the derivative of arctangent is this part. So if we let this be our function and this be the derivative, that's recognizing that chain rule thing. All right, so we have arctan of x to the first power. So it's just worrying about the power rule here. Add 1 to the power, divide by the new power, put your plus c. Okay, so it's not too bad. So go ahead and do part B for your whisk. And I wanted to cover probably one more example. One or two, that would be fine. So just hang in there. All right, there's two ways to do this one. One way would be using pattern recognition. Notice this time it's different because we have a definite integral. We're looking at a specific area. I notice that the derivative of x squared plus 1 is 2x, so I'm going to have that correction of 1/2. Then I have x times this blob, okay, x squared plus 1 cubed dx. I corrected for the 2x part, so I have now 1/2 times and power rule, okay? So add 1 to the power, divide by the new power, evaluate it from 0 to 1. I'm going to pull out my constant so I don't have to worry about it. All right, so we have 1 plus 1 to the 4th minus 0 plus 1 to the 4th, 2 to the 4th, okay, which would be, that would just be 16 eighths, all right, minus 1/8, which would give us a final answer of 15 eighths. So that is pattern recognition. Now, this way is kind of neat. All right, we're going to do this U-substitution. So let U equal x squared. Oh, man. All right, let U equal x squared plus 1. Du equals 2x dx. So 1/2 du equals x dx. Now I can replace the x and the dx with 1/2 du. All right, the only other thing is these are our bounds. This is x equals 1, x equals 0. We don't have x anymore. So I need to plug those in. My upper bound of 1, if I plug that in for u, I get 1 squared plus 1, or 2. All right, if I plug in my lower bound into this here, I get 0 squared plus 1. So now I have new bounds. I changed it to a whole new function here. So I'm going to rewrite this integral. I'm going to pull this 1/2 to the front. So 1/2 the integral from 1 to 2 of, I don't have to write x dx anymore. I got that covered with a du. I don't have to write this cubed anymore because that's just u cubed. All right, now it's just evaluating 1/2 times, that would be u to the 4th, add 1 to the power, divide by the new power. Okay, evaluated from 1 to 2. So I have 1/8 times 2 to the 4th minus 1 to the 4th. All right, and we get the same number of 15 eighths. So both of these are pretty neat ways. Okay, I don't care which one you use, but you have to be able to at least complete one way consistently. All right, so we're going to finish up with a little bit of review here. Review the following antiderivatives. This is something you should recognize. Maybe if I write it like this. All right, or maybe if I write this one like this. And the last one, maybe if I write it like this. You should recognize these already. And if you don't, you need to review your trig functions. All right, but each of those, this one's just inverse or arc sine, I don't care, whatever one you want, plus c. This one's equal to inverse tangent or arctangent of x plus c. And this one is arcsecant or inverse secant of x plus c. So I wonder what the other ones are. All right, we'll see. We'll see. Have a great